Yes. So hello everyone, and I will now continue again with the list of projects. But these projects which I will talk about will be star clusters in the Milky Way with Gaia. Okay, so Gaia is a ESA satellite, a satellite sent by the European Space Agency, which basically measures for a billion stars their photometry, astrometry, as well as their spectroscopy. And we're going to this projects would be basically based on Gaia data. They've been done by earlier groups also, but these are slightly different. What I'll talk about now. When we go to observe the Milky Way, this is what we see from the Earth, right? And the basic problem is that when we are looking at the Milky Way, since we are inside the Milky Way, right? Therefore, our view of the Milky Way is an inside out kind of Milky Way, right? Because we are seeing it from inside. And hence, it is very difficult for us to reconstruct our galaxy, to actually know what is our galaxy like, because we are inside it, right? It's like you are inside this room, and how will you find out the shape of this building, right? What does this building look like? You are already inside it. And so, therefore, the problem is we are living inside out. From inside, we are trying to see the view from outside. And at present, with no technology, we have not even gone totally outside our solar system with spacecrafts. So, therefore, maximum we've gone is up to Pluto's orbit, not beyond that. So, obviously, we cannot see our galaxy like this, so that we have such information of to what does our galaxy look like. And that's why when we want to study our galaxy, it's a different kind of a problem because we are seeing it from inside out. We do not know how is it this thing. Now, what were the earliest attempts to actually study the galaxy? I showed you that first picture, which some of you who are lucky enough from places where you can actually see Milky Way in the night, maybe in some of your hometowns you can see it. Here you definitely cannot see it. So the question was, how could one make a map of the Milky Way? So the earliest studies were made by Herschel, which Sir showed you in the morning also. And basically, he put an assumption that if you assume that all stars have the same brightness, so any faint star, you say it's further, any brighter star, it's closer. And he used this kind of a method to find out. So the center part is where we are positioned. And he said that these are the kind of shape of our galaxy. Well, obviously, this assumption of his was wrong, but he did get some kind of a shape. And if we actually look in this thing, if we know this is actually the shape of our galaxy, what Herschel looked at was only this part of the galaxy, which is our neighborhood, just the area around our sun. That is the area which Herschel was studying, just here. And this is the band in the sky. And like Sir told you in the morning, the basic problem is what is called interstellar absorption. Because we have lots of gas and dust also in the galaxy, so we cannot see certain part of the galaxy. Like for example, the center of the galaxy, there's lots of gas and dust over there, so we cannot see these regions. We only see this certain amount. Beyond this, there is so much of gas and dust that we cannot see anything. And that's why we only see this part. Now, the next attempt which was made to find our position in the galaxy was done by Shapley. Now, Shapley, in a way, is a Copernicus for the galaxy. In the sense, he actually showed us our position in the galaxy. And how did he do that? He did that by basically observing these things which you see over here, these balls. These are what are called globular clusters. I will show them to you again. But these are globular clusters. So these are present throughout the galaxy, and basically it's a cluster of many stars, 10,000, 20,000 stars. And that's why this is very, very bright. So the problem which I told you about interstellar absorption, that does not play such an important role with globular clusters because they are very bright, they have many, many stars. So even in spite of the fact that there is interstellar absorption and the globular clusters are far away from us, in spite of that, we can see them because they are made up of many stars, right? And therefore, what Shapley did is he observed all these globular clusters. Now, there are methods which we have spoken about in earlier workshops as to how to find the distance and age of globular clusters. But you can find out the distance to globular clusters by observing. And therefore, what Shapley did is he observed some 80 globular clusters and found out their distances. And therefore, he mapped these things. Where are the globular clusters? Where are they distributed? And found the center of that. And what he found out was very important. He found out that these globular clusters are a distribution, and the sun is not in the center of the distribution, which is a very correct conclusion which he made, because the sun is not in the center of the Milky Way. The sun is 2/3 away from the center. It is somewhere over here. So what happened is he did the globular cluster distribution and found out that the sun is somewhere over here, right? So that was correct what he did. So here you have Shapley. This is in the 1920s. So you can see here in these are the coordinates X, Y, Z, this galactic coordinates. Based on this, he found out where are these globular clusters located, and he found out the sun is over here, and globular clusters are distributed like this. Their center is somewhere over here, which should be the center of the galaxy, but globular clusters are over here, and hence what he found out that the sun is not at the center of our galaxy, right? So like for example, Copernicus found out that Earth is not the center of the solar system, right? Copernicus found out that Earth is not the center of the solar system. Exactly in the same way, Shapley found out using globular clusters that the sun is not in the center of the galaxy. And basically he found that out by seeing this globular cluster distribution, right? Seeing where are globular clusters distributed. So a globular cluster looks something like this, okay? And that's why I told you it's made up of many, many stars. It's very bright. And therefore, in spite of gas and dust in the galaxy, you can see very far away globular clusters because they are very bright. And hence they are very beautiful also. I don't know whether tomorrow we may manage to see some globular clusters when we go to observatory. It depends on the sky. We will see. But he used his 93 globular clusters and plotted it. So by then we already knew that this is our galaxy. The sun is not at the center. It is somewhere on the outside. This is the center of the galaxy, and this is our galaxy. So our galaxy looks like a disk galaxy. If you see it from here edge on, it looks like this. If you see from top, it will look like this. And that's how we know that. Now, what you can see in this is, you can see that the galaxy also has spiral arms. You see spirals. Now, how do we find out the spiral arms? Now, the spiral arms are basically made up of young stars. So that is why in our galaxy, if you can find out where are the young stars, they are the ones which make up the spiral arms. So if you can trace the young stars in our galaxy, they will be tracers of the spiral arms. So in short, to understand the structure of the galaxy, we have to find out tracers. What is the tracer of the spiral arm? What is the tracer of in one of the earlier workshops, students under Professor Deshpande are still doing rather a project on tracing spiral arms through pulsars. But pulsars are old dead stars, right? But they are also good tracers of spiral arms. Similarly, young stars are also good tracers of spiral arms. Now, what are clusters? Clusters are groups of stars. So we know that stars, when they form, they basically form in groups, because you have a giant molecular cloud which falls in its own weight. The gravitational energy is more than thermal energy. The mass of the cloud has to be at least 1,000 times the mass of the sun. Then this thing collapses, it breaks into pieces which form individual stars, which are clusters. And therefore, what we know is that stars are not born in isolation. They are born in groups, and all field stars are clusters, were originally in clusters. Like our sun also must have been born in a cluster. Later on, the clusters disrupt and the stars go away from one another. So a star cluster is basically a sample of stars formed from the same molecular cloud, where all the stars have the same age, chemical composition, they are at the same distance, they only differ in mass. And therefore, what we are going to talk about today is, because for these clusters, for the star clusters, it is possible to find their age, distance, and extinction, that is the amount of gas over there. Hence, they are very good tracers for Milky Way. So if we want to look at the galaxy and build the structure of the galaxy, we can use star clusters very well, because star clusters, for them, we can find out the distance and age, right? So let's say, for example, in this classroom, for each of you all, I know how to measure my distance to you, and I know how to measure your age, right? So then I can actually make a picture of this room, that in this room, who is sitting where, right? What is my distance to them, and how old are each of all of them, right? So if I want to find out in this room who are the students and who are the teachers, right? I have a method of finding out the age. So I can use that method to actually find out what is the, what is the structure. So I can say that these are the students and those are the faculty or Joby, whatever else. So that's the method which is used to actually, so we are trying to use star clusters to build up, make a build up of Milky Way, right? So if I know that certain group of star clusters form, they are very old, some are very young, but some are located here and some are located there. So I can build up a theory to say why is that kind of a distribution there, right? So what are the types of clusters? Like I told you, there are stars formed at the same distance, same time, chemical composition. They differ only in mass. You can have star clusters like this. This is an open cluster. If you've seen Pleiades, Kritika, you can see that with your eyes in the sky. Okay, that is a set of 5 sisters, and this is a globular cluster. So these are called open clusters. This is called a globular cluster where you have more stars close to each other. Globular clusters we already spoke about. They have at least 50,000, 1 lakh stars. They are very old objects, but they are very bright. Good to see. Open clusters, like I told you, Pleiades. These are made up of lesser number of stars, but the difference being that these are young stars and hence they are very bright. Okay. And so this is Pleiades, Kritika, which I told you. In the sky in winter, not just now, but in winter, if you know how to find out Orion constellation, this is Taurus, and near Taurus you have this M45 cluster, which is Pleiades, this one, Kritika. Okay. There are also associations or groups of stars which move together. We won't talk about them. Now, the important thing about these star clusters is that open clusters are on the plane of the galaxy. They are located at the plane of the galaxy, but globular clusters are not on the plane. Okay, they are up and down the plane. They are in these regions, So the other important thing about star clusters is we see pictures like this. So you think that they are stationary, like you all are all sitting in this classroom, not doing anything. But actually, in these star clusters, all these stars are moving. They are not static. They are actually moving. So they are like dancers over here, which you can see, which we are just seeing a snapshot. So we think they are stationary, but in reality, they are actually moving, right? So we have to actually even see the movement. How can we measure the movement? The movement is measured by, for example, I observe all of you all just now, then I observe you after 5 minutes. By then I see Asghar has moved over there. After some time, I see Ibtisam has come over here, right? So for each star, I take a shot now, I take an image after 5 minutes, I take again after 5 minutes, and in that way I can see the movement. Who has moved where in this classroom, right? So that's exactly what Gaia does, because Gaia very precisely measures position. So at different time steps, I measure the position, and with that I can measure the velocity. So Gaia directly gives you velocity data for individual stars. Now, once we know the motion of individual stars, there are many things we can do with them. You can study the dynamics in star clusters, because the star cluster is made up of many, many stars. You know their velocities. You can do that to study many things. Like what we saw yesterday was initial mass function. That means how is the mass distributed in those clusters? Mass segregation is how do the stars get shifted depending on their masses, and different things. Like for example, what is the effect of molecular clouds? If you see that the velocities have changed, it could be because of molecular clouds or tidal forces, or you see what are the binaries in that cluster and you see how do binaries change the evolution of the cluster, or stellar evolution. So all these different things can be studied when we know the dynamics of the star cluster. We know the velocities. Now, these in earlier workshops, we had done this thing that for star clusters with their observations, we can find out membership, which stars are members of the clusters, what is their distance, what's their age, what is like this. And this is a diagram which is called color magnitude diagram. This is called the HR, or the color magnitude diagram of star clusters. It's a very important diagram. It has the brightness of the stars in one filter, MV, and it has the difference of brightness of the stars in 2 filters. So for example, this is the blue minus visual phase filter, B minus V, and this is the V filter. So you plot this, and these are called HR diagrams. These are very, very important in astronomy. And basically they are important because on the basis of this, if you can plot HR diagram of stars, you can get their mass, their radius, their age, and all the important parameters, and their temperature, all important parameters for stars. And with Gaia, we can actually make HR diagrams of stars. Now, there are many catalogs of star clusters. These are earlier catalogs of star clusters. So here I'm basically trying to describe earlier work which we had done. Basically, this is an older catalog which is of 2013, where basically they had in the cluster written the position of all the star clusters. And in that you can see here they have plotted. The blue ones are open clusters and the red ones are globular clusters. And you can see that these are marked in this thing to see all the positions in the galaxy. What you can see in pink and blue and all that purple blue, these are all spiral arms. So you are using them to find the spiral arms. This circle over here is the circle of the sun, where the sun is located. Now we have the star's velocities. There are what is called radial velocity, which is the velocity in line of sight. This we get from Doppler effect. So if you measure the spectra, today in the morning you saw Timothy Hamilton showing you spectra. And with the spectra, if you can see what is the delta lambda, the shift in wavelength because of motion of the source, you can find out this quantity, which is called the radial velocity of stars, or it is the velocity in the line of sight. The other velocity which we find out is called the tangential velocity, which is in the plane of sky. You see how is a star moving. That is called the tangential velocity. With that, we can get the space velocity. We use radial velocity and tangential velocity to get the space velocity. Now, how do we measure? This is what is called proper motion. See this star. Supposing I looked at this just now, and then I saw it after some time, say after 6 months, and I see the star is over here. So I measure this shift, and this shift is called proper motion, right? So let us assume that these blue stars are far away behind, so they are not moving so fast, but this star is moving faster, and this movement is what I measure, which is called proper motion, right? Which Gaia measures. So this is animation is not working, but this is Ursa Major, where each individual star is moving in a different way. Okay. Now, Gaia actually measures positions of stars very, very accurately, which is the accuracy of a few microseconds. Microseconds is what? It means that if you have an atom, the first electron orbit is called a Bohr orbit. So if you were to see an atom with a Bohr orbit from a distance of 1 meter, that if you can see that orbit, that kind of resolution is what this satellite gives, Gaia. It's crazy. It's really, it's for example, if you had an astronaut on the moon, you would be able to see the astronaut from the earth. It is so well you can see it. And you can see it so well because the satellite is in space. Okay. So in space, there is no atmosphere, no turbulence. So you can measure all these things very nicely. So this is just a description of how astrometry has improved with time. We have been observing things more and more accurately. But the best way to measure is through space. Space, the advantage is you can see the whole sky, right? You can see northern hemisphere, southern hemisphere, everything. A telescope in space is stable. There is no temperature, gravity variation, no problem. And because there's no atmosphere, there are no variations. So the astrometry or positions are very, very accurate. Now, the first satellite sent in space was Hipparchus, which is in 1893, where it measured the positions of 1 million stars. But after that, the next satellite, so it measured the space velocity with very good accuracy. Now, like I told you, there are many star cluster catalogs and which actually measure these things. Now, if the earlier way, this is earlier work which we'd done earlier in which got published later. Okay, was we actually measured the latitudes and longitudes of these are for star cluster catalogs, and you see that there are certain peaks coming. Okay, in galactic longitude, and this is basically coming along the spiral arms of the Milky Way. Similarly, if you can actually plot them and see in longitude, how is the age distributed, how are different factors distributed, and you can actually use this to find the spiral structure of the galaxy. So if I know different catalogs, different star clusters, I can actually plot them and use them to find out where are the spiral arms of the galaxy, right? And that's what people have done with star cluster catalogs. We can also plot these catalogs in terms of age, right? Well, how is it distributed in terms of age, and what is this thing? We don't have too much time to do that in lots of detail, but I will think here. Now, what work we did was that we used the catalogs to actually do something called k-means clustering, looking for groups in the catalogs. And when we look for those groups, you can see that there's an earlier catalog called by this author called Dias, and we plotted every parameter versus every parameter. That means longitude versus latitude versus diameter versus galactocentric distance versus age versus numbers. And when we plotted this, you can clearly see that this is a statistical tool. Tomorrow you all will do a little bit of statistics, where you can see that there are actually 5 groups of clusters. You have 1, 2, 3, 4, 5 groups of clusters. You see of different sizes. This one is made up of 73, 299, 374, etc. Where they have different characteristics. You can see their sizes are different, the ages are different. Here are the ages, and the galactocentric distance is different. So we can see that there are different clumps or different groups of star clusters, right? We did this with another catalog also, this catalog Karchenko. Again, we got 6 different groups. In the earlier one, we had 5 different groups. And we did with another catalog. Here we got 4 different groups of catalog of this thing. And these can be actually used to understand how did the galaxy form. Because of all these different groups, you can see all the different groups formed at different times. This is of different ages and at different positions, different galactic latitude and longitude. You can see that this is how the galaxy actually formed. And we use this to do this. So this was earlier work which we did. But now this was done earlier to study the galaxy structure. But now we can use Gaia data. So in the projects which I'm proposing, we can actually use Gaia data to study star cluster catalogs in the same way. Only that this is much more accurate and better than the earlier data. So this is the Gaia satellite, which is sitting at L2 point. L2 point is the Lagrange point where the gravity of the Earth and the Sun are balanced. So this is the L2 point. See, this is the Sun, this is the Earth, this is the L2 point. This is where Gaia sits, as well as you can see here, this is James Webb. James Webb is also over here. L1 is meant for observatories which want to observe the Sun. So Aditya L1, which ISRO is going to launch next year, will be at L1 position. These ones are all at L2 because these do not want to look at the Sun. The Sun will burn the detector. We need to be there. And they have orbits of this kind over there. So with Gaia, we actually have data of RA, DEC, which is coordinates, parallax, radial velocity, proper motion RA, proper motion DEC. And with this, we can rebuild the structure of our galaxy. So what does Gaia do in star cluster study? First of all, you can use it to detect clusters, to find a cluster. The next step you can do is you can do it to find out cluster members, which stars are actually members of those clusters. And you get membership for all the stars. Gaia is unique because it has full sky coverage. You can see the whole sky. It has a faint limiting magnitude. It's homogeneous, accurate, and it gives you astrometry, photometry, as well as spectroscopy. So with Gaia data, this is work done by these other authors, Kent and Gordon. You can see that here they have actually plotted 1,229 clusters in XY plane with the spiral arms to show you the location of the spiral arms and where are these clusters which they actually found, right? And there have been the last data release is called the early data release 3. The data release 3 itself is going to happen on 13 June. Very soon, it's going to happen, and that's where new data will come out from Gaia. So I will not, okay, I can see this if you want. So you can see with Gaia data, you can now actually get motions of all the stars which make up the Milky Way. I am not going to do that now because we don't have, okay, we can see that. Okay, I can show that to you. You can see it over here. And you will see that with Gaia data, we can see the individual motions of stars. And that's what you'll see over here. Okay. So you can see over here This is how Gaia is actually looking at stars. There are 40,000 stars in the galaxy, and you can see it. Okay. So you can see these are the images of the stars, and you can see that Gaia is, look at it, Gaia is giving you data on velocity. So you can actually see the motions of individual stars in the galaxy. Where are they moving? Okay, so you can see over here, each individual star is moving, and this is data of 40,000 stars, but actually Gaia gives you data for 1 billion stars. So in this way, you can actually see the motions of these stars. Okay. So we'll go back to this. Yeah. Okay, so you'll actually see this. Similarly, with Gaia data, we can actually see the motion of the solar system, of the sun, and acceleration of the sun. How is the sun? See, now if you want to even see how is the sun moving in the galaxy, with Gaia data, you can study that because the motion will get reflected in that. And you can actually observe different parts of the galaxy. So I will now directly show you as part of this thing. Where is the Jupyter notebook? Yeah, okay. So I'm going to show you a Jupyter notebook, right? Okay. Where we are going to use catalogs to actually plot the position of open clusters and globular clusters using Gaia data. Okay. Now, those of you all who have laptops with you all, if you have a Jupyter notebook, you can use Google Colab, you can use whatever you want, and you can come onto this thing. So I will share this Python notebook with you all later on in your email. But at present, you can just look at this notebook and try to understand what is it doing, right? So like I told you, what I showed you in those earlier papers, the work of Shapley, for example, where he plotted globular clusters in the galaxy. We are now going to plot it using Gaia data, okay? So I hope you'll understand these normal commands. This is in Jupyter notebooks. If you want to use NumPy, we are using NumPy, we are using Pandas, and we are using Matplotlib. So you'll import NumPy as NP, Pandas as PD, and Matplotlib PyPlot as PLT. Now, yesterday, Sir spoke to you a little bit about how do we get astronomy data from something called Vizier. Okay, when we did virtual observatory tools, Vizier is a source from where you can get data which is already published. And therefore, using a Python notebook itself, you can import this package, which is the Vizier package. And so AstroQuery and AstroPy, these are two packages on Python, which have specifically been provided specifically for astronomy, right? So like even Timothy Hamilton mentioned to you today, that most of the software which is used by professional astronomers is all open source software, right? Open source means it is freely available to everyone. And even the code for the software is shared with everyone. So that if anybody wants to contribute, supposing there's some code in which you want to get some improvisation, you want to improve it, you want to do some differences, then the spirit is very good. It is open. I tell you what I know. I will show you how I'm plotting this, right? I will share this notebook with you. And if you want to make some improvement in it, you think that there is something I am missing on, or you want to plot something else. I have plotted open clusters. So maybe you decide to plot pulsar data, right? Or like I said, students with Avinash Deshpande, in the previous project, they were doing one pulsars on the spiral arms. So you may do it for pulsars, you can do it for any other objects if you decide to do it. You can use this notebook itself because I am giving you the notebook. Only you have to edit the notebook, change whatever you want, and plot whatever you want. The only thing I need from you is that you share what you do, so that you share it, so that then a third person can use it and further improve it or make changes. Obviously, for credit, when I do my work, I publish a paper, I get credit because I have published the paper. You take it, you add in your thing, you may publish a paper, you get credit for that. Then when you share it, the other person who uses your paper will refer to your paper, will also refer to my paper, and then improve on that paper, right? So in astronomy, in many other sciences it is being done, that people freely share what they have done, so that others can further improve it or make changes to it. So that's why, like how this Python notebook, I can share it with you. You can add whatever you want and improve it and do it. So this is all what is called open source, or what is called Creative Commons license. We share it with anybody who wants it. So here you can see is this is how we query catalogs in Vizier. Okay, you can run this file yourself. So when you run it, you will see it. We can actually get a query. I can query a catalog. Now all catalogs in Vizier have some number. So this catalog is sitting over here. Okay, this is the journal. This is the journal Astronomy and Astrophysics. This is the issue number. It's the paper number, whatever, the table. So in that way, you can query a catalog if you know what is its number. And once you query it, you can see that I can actually, here you see, this is the table. So I can check out what are the columns of the table. There are many more columns in this table. If you want, I can actually, I can show it to you 1 minute. So you have this table which has many. Here I'm only listing some columns, which is the column for cluster number, RA, deck, galactic longitude, galactic latitude. So here you can see is for all these clusters, I am mentioning what is the RA, the deck, longitude, latitude. So this is my data. So you can see the data has 2017 rows and 5 columns. Now what do I need to do? This is an RA deck, longitude, latitude. I want to convert it to XY. If you remember in that plot, I showed you XY plots. So I need to convert it into plots. And here, if the plots I do, you can see over here, I am using a package over here called AstroPy import. This is coordinates, right? So coordinates is a further library in AstroPy which will convert coordinates. So you import this thing called SkyCoord, and we are inputting galactic longitude and galactic latitude. And with that, we will find out XY coordinates. So here you can see is we found out the XY coordinates of this, which is this thing. So here first I'm plotting it with longitude and latitude, galactic longitude and galactic latitude. So you can see over here on x-axis is the longitude, on y-axis is the latitude. So this is the position of all these clusters in the galaxy, seen from down, right, from edge on. So this is longitude and this one is latitude, which you can see over here. So this is for open clusters. So we are seeing that open clusters are plotted like this in the galaxy. There are lesser over here, and there we are seeing it like this, and that's it, right? Now there's another catalog, which is a new catalog, last year, 2021, which is a catalog of globular clusters. So this one, the first one, blue, was open clusters. Now I am downloading the catalog which has globular clusters. And these globular clusters are in this catalog, which the number is this. Sorry, this was for open clusters. Now this is the catalog for globulars. So I'm querying this. And here again, I'm taking the data. I'm getting the RA deck. These are all globular clusters. So I have 170 globular clusters in this catalog. Now what I'm doing is, again, I will use this coordinates package, which is there in AstroPy, so that I convert this to, I take this thing. And here you can see I have overplotted. This is here showing you, blue is showing you the distribution of open clusters, and red is showing you the distribution of globular clusters, right? Now I can make my plot even look better by actually using an image of the galaxy, which Gaia itself has created. So we are here, I'm doing the same thing. I'm plotting this on this. There are different projections. We won't talk about that, but there are different ways of projecting data. So blue is open clusters, red is globular cluster. Now this is the Gaia sky map. Okay, using Gaia data, you can actually plot the galaxy. Okay, this is using Gaia data. This over here, you see, this is called the small Magellanic Cloud and the large Magellanic Cloud. This can be only seen from the southern hemisphere. So if you go to Australia, New Zealand, places like that, you will be able to see these objects. But this we cannot see from our skies because we are in the north, right? So this is only meant for southern skies, LMC, SMC. And you see now on this image, I can now plot the position of these things. So if I take this thing, here is my image. I will share this so you can run it. I can run it here. This is your image. And here, you can plot this over here. right? So you can actually plot this. If I want, I can also look at this over here. So this is the galactic. I can actually plot the coordinates of this and plot it in that way so that you can actually see the latitude placed over here and you can see the position, right? So the assignment I had defined was actually, I'm giving you the open cluster catalog, globular cluster catalog, as well as this Python notebook. And you have all this. Now the question is, how can you, for example, plot it with spiral arms? So for example, if we want to look at the spiral arm, if you look at this thing, I showed you a plot, right? Here, for example, where we have actually converted this to XY coordinates. XY coordinates are very easy. You just have to do L into cos alpha, cos delta, and sorry, you just have to do cos L. You have to use the galactic latitude longitude to actually get a position in XY coordinates, and you can use that to actually plot the positions, like in this thing. You plot the positions of open clusters and globular clusters in the galaxy so that you can plot spiral arms. The other thing you can do is you can also look for star forming regions. That is regions where you have excess of clusters, right? So there are some parts of the galaxy where there's lots of star formation taking place. There are some parts where there's lesser star formation. If you actually see even the image of the galaxy over here, right, you can see here is the galaxy. You can see that there are some parts which are brighter, some parts which are duller, some parts where there's more star formation, some parts where there's less star formation. So the idea is to use these catalogs to actually look for the regions where there's excess star formation, lesser star formation. Similarly, for the spiral arms of the galaxy, where are the spiral arms of the galaxy, and where are different structures over there, right? This is a very early paper. This is more than a 100 years old paper, where again star clusters were used to find this. But what I would expect or hope as part of the project would be to actually use. I will share, like I said, I will share that notebook with you, and we will use it to actually, yeah, we will use it to actually look for the distribution of these clusters, as well as look for clumps, clumpy regions within these, where you have excess of clusters, or you have, like there are many other features which you can see in this. You can clearly see that the galaxy kind of flares. You see over here in the center part, the distribution is thinner, right? They are thinner. You don't have many clusters which are outside the plane, which are up or down, not many. But as the distance from the center increases of these clusters, then you see that there are many more clusters above the plane and below the plane, right? So what I would want of you as part of the project is that you use these catalogs and plot them in different projections on the galaxy, and use that to actually look for structure, not just spiral arms, but also look for specific star forming regions and other substructures which you can find within the galaxy. So for spiral arms, you will have to actually look for data for the spiral arms. Similarly, for star forming regions, you will have to look for data of which are the key star forming regions in the galaxy, so that you can plot these clusters in those regions and see where do they belong, right? So I'll stop over here and I'll take questions. Okay. So if we have any questions, you can please ask. Here also, if we have any questions, you can ask, and I'll stop this share. I will mail you all this Python notebook, okay? And you'll be able to run it yourself and this thing. If you, for Python notebooks, you'll need to do conda install for that. If you don't have that, then you can also use what is called Google Colab. So if you have a Gmail account, right, please Google Colab and see how to join it. And you can You don't need to install any software. Without installing any software, you can directly use Google Colab and try to run this notebook, for example, with that, right? Yeah, so I think TP saying that's it. How do we register for the project? So tomorrow or today, whatever, I will share a Google form where participants can actually register for the project. I'm just waiting for all the projects to be listed clearly. And based on that, you all can, once you all register for the project, then you can get in touch with whomever you are doing your project with, right? And I'll tell you who are the mentors for which projects, which are the projects which are listed. And based on that, you can select your project and, you know, you all can make your own groups, social media groups, etc., with which you all can start work on the project, right? What about the talk? Please ask me questions about that. Yeah. Are there any questions? Here, any questions? Thank you. Welcome. Are there any questions? Yeah.
रीजन क्या है?
Similar, जो डस्ट का कोहरा रहता है, फॉर एग्जाम्पल, तो आप देख नहीं सकते हैं, राइट? तो इन द गैलेक्सी itself there is lots of gas and dust. So when I'm looking at something far away, I cannot see what is far away because there is dust over there. I can only see what is close by. And I may think there is nothing over there, but actually there are stars over there, but I cannot see it because there is gas and dust. So often when we are looking at the Milky Way also, we think there's a black patch in the sky. But actually that black patch is nothing black. It's just that there's gas and dust. So I cannot see the light which is behind it. So that's the problem.
तो वो natural है, मतलब
That's natural, yes. वो natural है. लेकिन उसको measuring that is very difficult because to see dust, how can we see the dust in this room, right? That is difficult. So there are methods to do it in astronomy, but it is not very easy. Instead, generally, dust is a very big problem because, like I said, you cannot directly measure it, observe. You have to measure it indirectly, right? So it is a bit of a problem, dust. Dust is a big problem.
Can you say this is due to the atmospheric refraction?
So yeah, if you're looking from the Earth, then yes, atmospheric refraction and all is there. But for example, if you're using a space telescope, then it's not that. Then it is dust in interstellar space. But there is dust here and there. Dust is there everywhere. So all of them will contribute. Right. Okay. Anybody else? Yeah. Okay. Nobody else? Everybody's tired. Okay. Fine. Okay. Okay. Okay, fine. I'll mail you all the notebook today itself, so you all can practice with that. And if you want to ask something, you can ask about it tomorrow itself. So I'll send it now to you all. Okay, I'll post you the mail for the notebook just now.